Welcome to this last session of the workshop. So we have 5 talks. The first one will be implicit form neural network for learning scalar hyperbolic conservation law, and it will be presented by Xiaoping Zhang. Please. Xiaoping, are you there?
Please wait. Oh, sorry. Can you?
We can hear you,
see?
we can see you, but we cannot see your slides.
Oh, okay, okay. Please wait. Okay. Sorry. Can you change to the next talk? Because my system. Oh, I should quit this system.
It's okay. Let's do that. I mean, Mike Douglas, are you ready?
I'm good. Yeah.
Okay, so we're going to switch to the next talk, and then at the very end of the session, we'll go back to the first. So the next talk is numerical calabiometric for holomorphic networks, and it's going to be presented by Mike Douglas.
Thank you. This is joint work with Subramania and Lakshman Narasimhan and Yidi Chi, who's now at Northeastern. So I've set out the problem in this first slide. It's a very central problem of string theory. There are several reasons why you should be interested in this, even if you know nothing about string theory. So I described Kähler geometry in the 15-minute talk. It is the simplest special case of Riemannian geometry that shows the features of the general case. So in the equation at the bottom, this second derivative of the function k is the metric. So the metric's determined by a single function, which is much simpler than Riemannian geometry, but still can have most of its features. So the type of problem we're solving is a specialization of Einstein's equation, Ricci flatness, and it reduces to the equation at the bottom, which is of Monge-Ampere type. This determinant, a volume form, equals a known volume form on the right-hand side. And I again refer you to the 15-minute talk for more details. So this has been studied over the years by a number of mathematicians and physicists. And the technique used in much of the work is not like what you may have seen of numerical relativity and the rest, where you have some simplicial decomposition. Rather, we use the fact that we have an explicit, as this defining equation, a hypersurface in a projective space. We have an explicit equation defining the surface, so we can basically treat the surface in terms of explicit basis functions, sampling points. And there's a natural parameterized family of metrics, this equation here, which are in mathematical terms the pullback of the Fubini-Studi metrics on projective space. And in simple terms, log of a general polynomial of a fixed degree. And then to find the best approximating metric to Ricci flatness in this class, there are a number of interesting algorithms. And then I should say this is a topic of again, great interest to algebraic geometers. And there's a lot of analytic results. And that makes it in some ways good for the type of benchmark problem that was mentioned earlier. And so Donaldson in particular developed an exponentially fast iterative scheme, which is very interesting. One can also just take the error with which this equation is satisfied and minimize its norm, as is done in most PDE work. And you can do integrals by sampling. And all this is very straightforward to implement using machine learning software, because it amounts really in this formulation to function interpolation, so supervised learning. Okay, so what was our work? So the general properties of this framework are not so different from other numerical PDE work, and in particular discursive dimension, and we're interested in a 6-dimensional manifold. So we can get acceptably accurate results with, say, 8 to the 6 parameters. But the previous work on this generally used codes written in Mathematica and such. And so machine learning software is already a very significant win. Now, the more interesting development that we made was to propose a class of feed-forward networks for these metrics and for holomorphic functions. And so I've written out the general feed-forward network here. We still have a linear transformations W, but the homogeneity of the type of function ansatz I had in the previous slide requires the activation function to be homogeneous. So we used a quadratic activation function. And then it turns out, again, this is not previously discussed in this algebraic geometric literature, but fits very naturally within it. And you could either take this to define holomorphic functions, generalizing to polynomials of the previous slide, the holomorphic network, or you could consider bihomogeneous combinations, such as a real part of Z times its complex conjugate. And it turns out that that second option, what we call a bihomogeneous network, works quite well for solving these problems. So a lot of interesting results, because again, there's a lot of analytic work that one can compare with in our paper. And let me just say a word about a result of probably broad interest in PDE. Is it the case that by representing the solution using a feed-forward network as opposed to a standard, linear basis or finite elements or the rest, do you systematically use fewer parameters? And of course, with very high dimension, the answer is yes. But 6 is moderate dimension, high enough that we're interested, but low enough that these general arguments may not get to the point. And we have pretty good empirical evidence that the answer is sometimes, that there are metrics that you save on parameters, but there are other metrics where you need as many parameters as the general ansatz. And here's an example of results graphed from the paper. So what would the number of parameters depend on? We can vary quantities like the shortest distance scale of the metric. So it's a problem with no boundary conditions, but by varying the defining equation, you can vary the shortest distance scale, which appears in the metric. You can vary the amount of symmetry in the metric. And then the various colors represent either the general ansatz with 2, 3, 4 degree. The est8 is an extrapolation. It was an analytic extrapolation to predict the error for a general ansatz with the same number, the same degree polynomials as these neural networks, 50 wide, 70 wide, 300 wide. And if you compare, say, the pink dots, the best possible, the green dots is a neural network with the comparable number of parameters, and the purple dots is a neural network with the same degree function representation, but factor of 20 fewer parameters. You can see very clearly this type of distinction where metrics with features on short distance scales, large ratios of scales, cannot be completely, as accurately represented. And so it'd be very interesting to have contact between the theoretical works on feed-forward machine learning networks and this type of empirical result. So I'll stop there. Thank you.
Okay, thank you, Mike. Okay, so the next talk is a data-driven method to compute quasi-potential, and it will be presented by Bo Lin. Bo? Okay. Bo, we see your screen, but we don't hear you.
Okay, so can you hear me now? Okay.
Yes.
Okay, thank you. Hi, my name is Bonnie. Thanks for the opportunity to present for our paper, a data-driven method for computing quasi-potentials. This is joint work with Chen Xiaoli and Professor Wei Qinren. In the work, we consider the process ST modeled by this stochastic differential equation. Here, F is the force field, epsilon is the amplitude of the noise, WT is a standard Brownian motion. In the work, we consider the case that epsilon is small. Then the quasi-potential with respect to the tract A is defined as the infimum of this path functional over path space. the path phi is connecting the thread A and the state X with time horizon T. Here, the quasi-potential is defined in the state space, which is usually in high dimensions. The quasi-potential is a natural generalization of the energy needed for the system to transit from A to X when the noise is small. More details regarding the importance of quasi-potential is referred to the theory by Friedrich and Wendell. Previous methods for computing the quasi-potential landscape, including the mesh-based methods and the path-based methods, suffer from the so-called curse of dimensionality. Our method is based on this decomposition of the force field. We decompose the force field into two components, where negative gradient V is referred to as a potential component, and the Gx is referred to as a rotational component. These two components are orthogonal to each other. One can show that under certain conditions, the function 2V from the potential component coincides with the quasi-potential amplitude and additive constant. In our method, we assume that we have access to the trajectory data. But the force field F is not known. Our goal is to learn the force field in the form of the orthogonal decomposition. So we will parameterize the function V by the sum of a neural network and a quadratic function. Here, the quadratic function is added to ensure that the dynamics is stable to a bounded and measure zero set. The other component G is parameterized by a neural network G theta. Therefore, the force field is parameterized in this form by the above two neural networks. The observation data set contains n trajectories from the deterministic dynamics. So the loss function contains two parts. The first part measures the difference between the learned dynamics and the true dynamics by performing numerical integration of the learned dynamics. So it is to reconstruct the dynamics as given by the data. The second part is to impose the orthogonality condition. Here, lambda is a parameter. In the numerical example, we will consider a high-dimensional problem. It is obtained by discretization of the Browser-Later equation. It is a PDE defined on the interval 0, 1 with the Neumann boundary conditions. So we will discretize the domain 0, 1 using a uniform mesh with 20 grid points and the central finite difference. Then the obtained system is in the 40-dimensional space, and it has one stable state. So we will take a beta in the equation to be 0.01 and 1 respectively. We will use these two neural networks in the parameterized force field. The observation data set contains 10 million data points by sampling 50,000 trajectories. So the computation is done in high dimensions. Here we show the cross section of the learned quasi-potential as a function of two variables for the different values of beta. Also showing are the snapshots of the paths from the learned dynamics. We can see that they agree well with the true dynamics. In summary, in this work, we propose an efficient and data-driven method for computing the quasi-potential landscape in high dimensions. Thank you.
Thank you, Bo. Thank you also for staying in time. Okay, so the next talk will be about optimal policies for a pandemic, and it will be presented by Yao Xuan.
Thank you. Hi everyone, I'm Yao Xuan. This is a joint work with Robert Belkin, Jiexun Han, Raymond Hu, and Hector Saniseros. In the past 1.5 years, COVID-19 has a significant influence on our life. The most powerful tools to fight with the COVID-19 are lockdown policies and vaccination policies. To find the optimal policies for a pandemic, we need two steps here. First, step one, we need to build a model to model the pandemic and also the relationship between the pandemic and policies. Here we use the stochastic game approach to model the pandemic. Second, we need to solve for the model. Here we propose a deep learning algorithm to solve for the model. Now first, step one, we propose a multi-region SEIR model to model the pandemic. For each region, we have 4 groups of populations: susceptible, exposed, infectious, and removed. We model the change of each group of population by stochastic differential equations. Here we have the controls, lockdown policies as L, and health policies as H. And then we assume that the planner of each region is trying to minimize its region's economic cost defined in equation 1. We try to find the Nash equilibrium of the stochastic game and find the optimal policy. Step 2, to solve for this model, we first derive the HGB equations for the stochastic game. As we can see, the HGB equations are uncoupled nonlinear equations with the dimension 3n plus 1. It's a very high dimensional problem. We do not have a nice traditional numerical solver for this problem. So we propose the enhanced deep figure split algorithm, which is an extension of the deep figure split proposed by Handel in 2020. Here is the idea for the enhanced deep figure split algorithm. We would like to update the optimal policies for each region. We would update the policy stage by stage. We assume that in each stage, let's say n+1 stage, each region know the optimal policies for all the other regions in the last stage. So now in this stage, each region will assume that all the other regions are taking their optimal policies from the last stage. Then it could focus on its own policy and try to find the optimal policies in this situation. Then in the end of this stage, it will update its own policy. We do this stage by stage and until the policy converges to the Nash equilibrium. Compare with the deep figure split algorithm, compare with DFP. Our eDFP introduced additional neural networks to approximate the policy functions. By doing this in each stage, when we evaluate the policy function, we do not need to store or use all the results from the previous M stages. So it will reduce the memory complexity and the time complexity. Yeah, so that's the algorithm. For the numerical experiments, we did the stochastic game among New York, New Jersey, and Pennsylvania. Our numerical results shows the dependence of policies on parameter A, which represents planners' view on the death of human beings. If planners pay more attention to the death of human beings, they would like to spend more money on the lockdown policies to reduce the number of deaths. Our numerical results coincide with this intuition. When A is large, the planners pay more attention to the deaths, the lockdown policy is very strict. And when A is small, we do not have a strict lockdown policy here. The second experiment shows the dependence of policies on parameter theta. Theta represents the residents' willingness to comply with the policy. On the left panels, the residents are less willing to follow the policy. So in this case, if we look at the susceptible, in the end, the pandemic will get out of control. However, on the right panel, when the residents are more willing to follow the policy, in the end, the pandemic will be get well controlled. Yeah, that's the talk. Thank you.
Thank you. So now the next talk is reconstruction of pairwise interaction using energy-based model, and it will be presented by Carlo Lucibello.
Hi all, thank you. And yeah, I will present this work in collaboration with Christoph and Auer. We are both at Bocconi University, and essentially we'll discuss a classical problem in statistical physics, which is the inverse problem, where you have to reconstruct some coupling, some pairwise interaction, given some data samples. Let me first frame this problem in a more general setting, which is the one of knowledge integration. Maybe also is kind of trivial for this audience, but basically you have some data on which you usually train your machine learning pipeline, which is typically also black box, but you also want to introduce some prior knowledge that you have of the problem. This is because maybe you don't have big data, you have some small data sets, and so in order to perform good predictions, you have to leverage some prior knowledge, or because maybe you want to model in order to have some better understanding and some interpretability of the problem. So you can like insert your prior knowledge in different stages of your pipeline, in the training, in the preprocessing of the data, in the definition of the model itself, or in the loss function as regularizers maybe, or by just tweaking the final predictions from the model. In this work, we are mostly interested in a particular type of knowledge among the many types of prior knowledge you can have, and this is one concerning some probabilistic structure of your data. So we are given a data set, and the task is the generative modeling task, where you want to train some model from a parameterized family, typically, that is able to generate some new samples which are similar to the original data. There are many different models which are commonly used for this task. You have variation autoencoders, GANs, autoregressive neural networks, transformers, you have normalizing flows, and all of them have different strengths and cons, but for all of them, it is true that it's difficult to kind of insert some probabilistic knowledge, at least some generic probabilistic knowledge that you may have on the data generating process. This is why we rely on a more less used model, which is the family of energy-based model, which allow for something which is very simple, but in practice different to achieve, which is model composability, meaning in probabilistic terms, meaning that you can create a new distribution just by taking the product of two distributions, one of which may be this encoding your prior knowledge of the problem, so as a simple and specific structure. The other one could be maybe a black box model. So in our case, we investigate a specific energy-based model where we model our data with a simple part. So this is our prior knowledge. So the presence of some pairwise structure in our problem, and this is encoded by this term here in the energy model. And then we also leverage a neural network, which in our approach will be able to model the remaining part, the higher order terms in the data distribution. So, and this is graphically explained here. Sorry, I have a train passing by. So we know that there are some pairwise interactions. We know that there are also some higher order interaction, but we don't know the order of these interactions, which variables are involved. So we model all of the higher order terms with a neural network. And we train the whole architecture, this hybrid architecture, using a maximum pseudo-likelihood approach, because energy-based models are not easy to train using a maximum likelihood approach. We test our model in two different settings. The first one is a synthetic setting, where we generate the data from a spin glass model, which contains both order 2 and order 3 interactions. Then we try to reconstruct the order 2 interactions from the data. And we do that for different strength of the higher order parts in the generative model of the data. And so what we get is that while the pairwise model, when the higher order strength in the generative Hamiltonian is very small, the pairwise model, the green line, is good at reconstructing the data. But then, as you tune up the higher order interaction, the pairwise model becomes very mismatched and it doesn't perform very well, while our hybrid approach leverages the strength of the neural network to encode the higher order part. Another setting which we experimented on is in the protein domain, where you have multiple sequence alignments, so alignments of sequences of proteins within some protein family, and we model this data and then we infer the couplings, and the couplings, as has been found 10 years ago or more in the literature, the couplings are a good predictor of the residue-residue contact in the folded protein. So the task here is to predict the contacts when the protein is folded, and as you can see, the hybrid model is better than the pairwise one, which is the blue curve, which has been used in a huge amount of papers to model this kind of system. I mean, the pairwise model is very good already. So the POTS model is a good model of this kind of data set, but by also accounting for higher order interaction, we can squeeze some more performance from the data set. And that would be all. Thank you for listening.
Thank you, Carlo. So we can now go back to the first talk, which was on implicit form neural network for learning scalar hyperbolic conservation law, and it will be presented by Xiaoping Zhang. Yes, we see you. Yeah. Xiaoping, we see your slides now, but we don't hear you.
Is it okay?
No, we hear you and see your slide. Yes.
Okay. Oh, okay. Oh, thanks for your attention. I'm going to present our work implicit form neural network for learning scalar hyperbolic conservation law. This is a joint work with Tao Chen and Professor Lili Zhu. Deep learning techniques have been applied to mathematics and scientific problems, and a lot of excellent works on learning PDEs have emerged. The first attempt of solving PDEs can be traced to back to the late last century. Currently, there are at least two major ways to use deep learning for solving PDEs. One is the deep learning method, and the other one is PIN. Our work focuses on the solution of scalar hyperbolic conservation law, which can be expressed as follows, like this. Although the deep learning method and the PIN have achieved great success, they still exhibit poor performance in handling problems with strong discontinuous solutions, such as scalar hyperbolic conservation law. Our work is to propose a deep neural network based on this theorem, which states an implicit form for the solution of scalar hyperbolic conservation law, which is expressed in Formula 2. The net architecture and the sampling strategy of our network is the same with those used in the PIN. The key difference between our network and the PIN or deep learning method is the choice of the loss function. For example, the essential term we call the implicit form loss is constructed based on the Formula 2. This is the key difference. key difference. And the initial condition and the boundary the initial loss and the boundary loss are the same as those used in the pin. Next, we will show some examples to compare the numerical performance between our network and the pin. First, let us take the one-dimension inviscid Berg's equation as an example with different initial conditions. The first row is one-step shock wave. The second row is a two-step shock wave, and the third row is about a sinusoidal initial data. In these cases, we find that our IFN can capture the shock wave very well, but the pin fails. The result of IFN is shown in the red line, and the result of pin is shown in green line. The last row is about a rarefaction wave. Since the solution is continuous, both IFN and the pin can produce accurate solutions. Next, we take the two-dimension with the Berg's equation with shock waves. From the first row, we can see our IFN can capture the two-dimension shock wave very well. The next two rows are related to LOWR model for traffic flow problem. The second row describes a traffic jam, which produces a traveling shock wave. And the last row describes the traffic state when the traffic light turns green, which is the solution is like a rarefaction flow, rarefaction wave. From this, we can also see our IFN can capture the shock wave very well, but the pin fails. Finally, let's make a summary about the pros and the cons of IFNN. The training of IFNN is much easier than that of pin, since it's not needed to need a lot to use automatic differential for computing the differential operators. But IFNN requires the target PDEs to have the specific implicit form of the solution. Though the scope of its visibility may not be as wide as pin. That's all. Thanks for your listening.
Okay, thank you all for this very nice talk. So we have some time for a discussion now. I think that there was a few questions that were put on the chat. Johan had a question for. I think maybe you.
Sorry, you got a question for whom?
For Mike Douglas, no?
Yeah. So, yeah, we had some interesting offline discussion on the chat. That I guess my question had to do mostly with the relevance of using a polynomial activation for the problem, and to what extent the polynomial activation can be a good choice to compare the neural network architecture with the baseline. That would be just looking at approximations using polynomials. And so, yeah, maybe Michael, you wanna say the answer.
Yeah, sure. I mean, the choice of polynomial here is actually kind of forced by the mathematics. We have to use this coordinate system on our manifold. We have to use homogeneous functions, and so we need a homogeneous activation function. But it's both natural, I think, for the usual reasons. For example, that the multi-layer structure allows representing structure at different length scales. The intuition that squaring, increases, doubles the degree tells you that you're getting exponential range of length scales that way. And then the usual problems with polynomials that they run off to infinity, they're badly behaved, are not really the case in algebraic geometry. So we actually, I didn't have time, but these homogeneous coordinates you use in practice by constraining to say sum of the squares equals 1. So you're looking at them as functions on a bounded domain. You're only taking polynomials of one fixed degree and so forth. And so the original ansatz without the neural network was very well behaved, and the neural network inherits that.
Thank you. Yeah.
Okay. I actually had a question for Bolin for the data-driven approach to compute the quasi-potential. I was not completely sure, maybe I missed it, how you actually get the data, because when you compute this quasi-potential, by definition, you are looking at a situation in which the probability, the quasi-potential gives you the exponential decay of the probability in the tail. So you have, it's very rare to observe these events. So how do you proceed to get the data to perform the training?
So far the data is obtained by sampling the path of the deterministic dynamics. So the computation of the quasi-potential relies on the data. So where you have data, where you can compute the quasi-potential well. So it really depends on the sampling of the deterministic dynamics.
So you mean you're minimizing the objective function, that's the Lagrangian formulation for quasi-potential at a given number of points, and then you use that to reconstruct the quasi-potential. Am I understanding correctly?
Yes.
How do you choose the points? I mean, it looks like you should have some kind of online or reinforcement learning strategy to do that. How do you use the endpoint when you do that? In your formula, there was UA of X. Could you pick the X?
So it depends on availability of the data. So far we didn't consider too much on how to obtain very effective data. So we are supposing that we have some data from the deterministic dynamics. So then we can compute it. And so to more effectively compute the quasi-potential, of course, the data need to be covered. Need to be covering the region that of interest. Of course, it is.
Okay, thank you. Joan, you had also a question for Carlos.
Yeah. So that, I mean, the result, I mean, the model that you introduced is very natural and very suggestive. And it also, of course, it remind me of some of the efforts on a different community, more on the machine learning side of graph neural networks, where people have also thought about, using some basic template to extract local interactions and then use learning to go for higher orders. And typically the roadblock that these methods hit is the fact that these things are pretty hard to scale, right? And so I was wondering if in your architecture that is there to try to grab these higher order interactions, how do you parameterize it, and did you think about how this thing would be scaled up to either maybe larger systems or maybe just going for higher orders?
Yeah, right. Since we don't do any assumptions of the result or on the residuals, so on the strength of the higher order interaction, so maybe they could be not small. So actually we use a neural network with standard initialization. And it is true though that this hybrid approach is not very robust. And we had to experiment a little bit with L2 regularizers, with the width and the depth of the neural network, and in many settings you experience a lot of overfitting. And we saw that also in some more recent experiments, we saw that the objective function is very relevant for that. For instance, we use pseudo-likelihood for training, but other techniques for training energy-based models, such as noise contrastive divergence or noise contrastive estimation, they seem to be much more robust. So yeah, I mean, it's a little bit tricky and some work is involved, but there seems to be like a path forward.
I see. Okay. Yeah, I think it's yeah, I can see what you mean. So anyway, I think it's an interesting model, and clearly there's still a lot of open questions to think about. Yeah. All right.
Okay, I think these were all the questions that were in the chat, if I look correctly. So I mean, you know, the floor is open for further discussion. If anyone has an additional question to ask, please unmute yourself and shoot. Okay.
Yeah.
Maybe yes, John, you had something.
No, I just go ahead.
So maybe I had one last one, maybe then for Xiaoping, which is I was not completely sure I understood which loss you used in the, you know, to solve the equation. So I understood that, you know, the representation that you made, this implicit representation, which is tailored to the fact that there is shocks. But what's the loss that you use then? Again, like how do you actually perform the optimization of the parameters? Which type of data do you use, and how do you optimize? I mean, what's the loss that you? Is just square discrepancy, or maybe this is something which is coming from other methods, but.
Oh, okay. We use the difference. The difference between our network and the pin are all the same. So the optimization is done by Adams and then LBFGS a second order scheme.
So that means you look at the prime, you know, on the fixed space-time domain, and you assume that you know the solution by other mean at some points on this space-time domain.
Yes.
Okay.
So spatial and the temporal domain.
Yeah. Okay. Okay. Thank you. Well, I think, you know, that's pretty much it. So let me thank all the speakers of this last session. I mean, since this is the last session, I think I should, you know, it's really my duty and my pleasure, in fact, to also thank the organizer, Lenka and Joan and Jan, for organizing this conference. It was quite an effort, and, you know, it's not made easy by the fact that it's all online, but I think it ran fairly smoothly, and it was quite informative. So thank you very much for that. And I guess that brings us to the end. I don't know if Joan or Lenka or Jan wants to add something.
No, I mean, just echo your just point. I mean, thank you. I mean, the conference is made by, you know, through the authors and everyone who helped preparing, you know, building the program. So thank you all. And it was very intense, but I think at least for me, I learned a lot, and I'll have a lot of homework to do, reading now in detail as most of the papers. And so, yeah, thank you all. And I don't know, Lenka, you wanna close the conference officially?
Right. I just want to say to those who are still here, like, thank you really a lot for staying till the end. That's quite some effort. And since it means you're supporting this conference, so please, you know, stay tuned, because next year there will be surely sometime in the fall the deadline for the submission of papers for next year. So please keep that in mind. Surely you are working on new exciting stuff, and just keep those that would be interesting for this conference for the deadline. And surely we will be, or the new organizers that we saw earlier today will be contacting some of you as referees, some of you as area chairs. So thanks in advance for saying yes and helping making the next year great as well. Thank you.
Okay.
Okay.
Bye everyone, and
Bye everyone.
have a nice end of August, and good luck everyone. Bye bye.
Bye bye. Ciao.
Ciao.